So we're looking at page 12 in the unit P packet. What we want to do now is develop a relationship that allows us to convert from polar to rectangular forms and vice versa. Right? So we learned already how to convert back and forth between rectangular and parametric. So now we're going to convert from rectangular to polar, and you'll see as we go forward that there'll be an expectation that you'll be able to convert from polar to parametric, right? And actually, in a lot of cases, we'll be using parametric equations that are composed of polar functions. All right, so a lot of interesting stuff coming your way. All right, so I included this diagram here because, one, I didn't want to draw it, obviously. If you look at the quality of it, I can't do that. But also, if you just look at a little section, just the first quadrant of a polar graph, without all the bells and whistles, if you were to plot a point in space, any point can be decomposed into horizontal and vertical components. All right, a horizontal movement and a vertical movement. X and Y are your rectangular coordinates. Ooh, my squiggly bracket game is weak today. All right, so this is rectangular. And these are the polar coordinates. All right, so we have two different ways of representing the same location. So the big question would be, okay, is there a relationship between the two? Well, we have a right triangle. A lot of great stuff happens when you have a right triangle. That's one of the reasons why you spent so much time learning about right triangles way back when. All right, the first and I think most obvious one is that x squared plus y squared is equal to r squared. All right, it's a right triangle, so Pythagorean theorem would apply. Now, if r is equal to 1, as in the radius is equal to 1, then you have x squared plus y squared equals 1, which would be the equation of the unit circle, which is why I was saying that the polar coordinate system is really just a mega unit circle. All right. We could also say that the sine of theta is equal to y over r, cosine of theta, x over r, tangent of theta, y over x. All right. Reciprocal functions also apply. All right. We could say cosecant is r over y, secant r over x, and cotangent would be x over y. All of these trig relationships are true. We can solve each one of these for whatever variable it makes sense to solve for. All right, so it just kind of depends on what you need. Now, if you look at the examples, just find the exact rectangular coordinates given each point. So we're given r and theta. In both cases, r and theta. So I need to be able to come up with an x and a y. It's about to crash on me, I think. We'll find out in a sec. We need to come up with an x and y given an r and a theta. All right, well, I'm looking at a couple of different possibilities here. Each one of these equations has an x, y, r, and theta in some capacity. All right, so we can make use of that information. For example, I can say y, if I cross multiply, y is equal to r times the sine of theta. I could say x is equal to r times the cosine of theta. Now, I know a lot of people don't like the reciprocal functions, but they do have value, and they're worth talking about. So that's what I'm going to do. I could solve this one for y and say y is equal to r over cosecant of theta, and x would be equal to r over secant of theta. A commonly forgotten property of proportions, the product, you might have learned this in geometry class actually, the product of the means equals the product of the extremes. It's a really fancy way of saying that the diagonals are interchangeable in a proportion, right? So, and you're like, a proportion? Well, any fraction could be, or any value could be created into a fraction or turned into a fraction by putting it over a 1. So that's all that's happening here. All right, I'm just not showing it. All right, so we have all that information. And so you look at what we have available, depending on the situation, you might go with one variation or another, but if you have a choice in the matter, you're probably going to say, based off of this information, looking at these two guys, that x and y correspond to r cosine theta, comma r sine theta. All right, I think I'm due for a resize here. You could do the same thing with the reciprocal functions too, but it's really just not, it's not necessary if this is going to work, right? But let's say you want to be as precise is not the right word. I'll get there. I'll find the word. Thorough. Ugh, it took all day for that, huh? So we would say r over secant of theta, comma, r over cosecant of theta. All right, so this is an either or. You don't need them both, just one or the other. And most people are going to be more comfortable with the sines and cosines, but there is a time and a place for secants and cosecants. All right, so let's tackle an example or two and see what's up. Finding exact rectangular coordinates. We have the r and the theta, so I need the x and y. All right, so x and y is going to be equal to r cosine theta, comma r sine theta. So we're saying 3 cosine 270, 3 sine of 270. All right, cosine of 270 is equal to 0. 3 times 0 is 0. Sine of 270 is -1. 3 times -1 is -3. All right. Now I'm going to just pop this on the graph below. All right. It's got a coordinate system. I'm sorry, a rectangular coordinate system overlaid upon a polar coordinate system. All right. So the idea is that if we plot in one system, we should be able to see how it jives with the other. All right. So if I plot, we have 3 270. All right. So 270 degrees would be down here. Now I'm thinking in terms of rings. All right. So I'm just going to draw out the rings. I have one. Okay. I didn't put my circle tool on. See just how able I am to draw right before it does the autocorrect. It's like, oh, so that's what you're capable of. All right, so this would be 3 rings. So I want 3 rings in the direction of 270. That would be right here. All right, so that's 3, 270. All right, but if you look at that in terms of boxes, your rectangular coordinate system, that would be 1, 2, 3 steps below the x-axis. So no change in x, but a change of y of specifically of 3 units down. So this would be 0, -3. right? So graphically, it works out. Right now, for quadrantal angles, angles that fall on an axis, it's pretty easy to identify. Like, for example, if you look right at number 3, I don't need to do any work, because if I just sort of reverse engineer and take a look at my question here compared to my answer here, hopefully you find it obvious that this should correspond to 7 steps in the direction of 270 degrees. I'll show you how to do it algebraically in a minute, but if you see that relationship, that's a good thing. All right. So we're still working off of that same fact for the second example. You just got to know a little bit more trig. Now, I haven't really gotten into the Desmos yet. You don't really need to know every aspect of trigonometry, but it does really help. All right, so -2 cosine -5 pi over 6, -2 sine -5 pi over 6. All right, the feedback I've gotten from this course, the several times, many times, any version of calculus that I've taught, actually, not even just this class, is that it's an easier ride if you know your unit circle trigonometry. Right? If you look at the end of this packet, you can see that there's a unit circle error completed once, so definitely take the time and look that over. All right, so we're looking at -2. -5 pi over 6 is a 30-degree reference angle in the third quadrant. Cosine has a value of negative radical 3 over 2 at that location. Sine has a value of -1/2 at that location. All right, so we're talking radical 3, comma 1. All right, so I'm going to plot this. 5 pi over 6, all right, so, this is what I was talking about before when I was saying you count in terms of pi over 12. So 1 pi over 12, 2 pi over 12, 3, 4, 5, 6 pi over 12. If I want to get to 5 pi over 6, I want to get to really 10 pi over 12, right? I'm saying right. This is a video. I'm saying right as if somebody's going to answer me. Yumpin' Yiminy. So this is the same as, and by the way, I do keep track of things that are like buzzwords or phrases in society. Right is a common one now. People do it all the time. You hear it in talk shows, everyday conversations. People finish a thought with right. It's always something, right? It's very weird. That's my observation of the day. And that'll date this video, because if I intend on using this like 20 years from now, people are going to be like, well, that word doesn't even exist anymore. So we have -10 pi over 12 is the same as -5 pi over 6. All right, so if we're counting in twelfths, we're up to, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi over 12. Flip it over the axis. That would put you right here. Now I want to go, I want to go 2 steps away from this angle. All right, so that would put me 2 rings away. That's going to put me right here. And my point's a little messy there. Well, the whole graph is messy now because I got a little cute with it. All right. So that would be -2, comma, -5 pi over 6. All right. This location here is pi over 6. This one is 7 pi over 6, which is the same as -5 pi over 6. All right, all interesting, useful information, but not necessary to get the solution. I'm just going to clean this up a little bit. All right, now the big question. There's always a big question now that I think about it. Is that equivalent to radical 3 comma 1? Well, radical 3 is about 1.7-ish, comma 1. So 1 unit, 2 units. Does this look like it could be about 0.7? Does this look like it's 1? Yeah. All right, so this is also, so or radical 3 comma 1. All right, so we get a nice visual to verify our result on the graph. All right, so we still want to be able to get away from actually doing it on the graph. We want to be able to have technology do it for us, but I don't really enjoy jumping into the technology without getting into the theory behind it first, because there's really no learning there, you know. I mean, students enjoy that. I don't as a teacher. All right. So for numbers 3 and 4, we want to be able to come up with polar coordinates given the rectangular form. So I have x and y. That's not a marker. X and y in both cases. I need to come up with an r and a theta. All right. Well, I have all this information here, lots of stuff. Not all of it is necessary, though. I do have a way to come up with r, though. So if we take a look at that very first equation, the one that we kind of glossed over and never looked at again, I can solve that for r. That's going to be equal to the square root of x squared plus y squared. So now I can come up with an r value if I know an x and a y. That's great. And I also have like tons of methods by which I can come up with a theta. All right, I have 6 equations that involve a theta. 2 of them are reliant strictly on an x and a y. All right, so that would be the tangent and the cotangent. So we'll need this one. Now, if I want to use the tangent equation and I want to solve for theta, I would take the inverse tangent of both sides. So inverse tangent of the tangent of theta would be equal to the inverse tangent of y over x. All right, a function of its inverse it cancels to the argument, and we're left with just a theta equal to the inverse tangent of y over x. Schmidge it down. I'm not going to bore you with the details on cotangent. I'm just going to say that would be equivalent to theta equal to the inverse cotangent, just following the same strategy, of x over y. You could find inverse, inverse sine of y over r, inverse cosine of x over r. You could do inverse cosecant, inverse secant, but that involves y's and r's, so you're relying on a prior answer. You know, there is the idea of you want to be efficient, but you also want to get as much credit. You know, sort of hedge your bet. You know, if you need to come up with an r and a theta, if you're relying on the given information for both parts, you know, to find r and then also to find theta, then you stand a better chance than if you rely on a previously computed answer. Because if you make a mistake there, you've made a mistake the rest of the way too. All right, so, you know, just a thought. Hopefully a coherent one. Honestly, I barely understood what I just said. So we'll see. Anyway, so r is going to be equal to the square root of 0 squared plus -7 squared. The more time you spend doing these kind of problems, the more you realize that this really is an unnecessary computation, because if you're on an axis, and if you look at a diagram, you see that, I mean, it's a little iffy of a diagram. It's kind of very faint, but hopefully you see that the rectangular coordinates coincide with the polar coordinates on the axes. They're exactly the same, right? So 7 steps along the x-axis corresponds to 7 steps along the polar axis. You know, that kind of idea, right? And then we have the theta. I'm going to go with tangent. So inverse tangent of y over x. So -7 over 0. Now we've touched on this inverse tangent stuff before. The inverse tangent function only exists on the interval of -pi to pi. I'm sorry, -pi over 2 to pi over 2. So we have to be mindful of that. We may have to use reference angles to come up with a true angle. However, in this case, we have undefined, right? Tangent function is undefined wherever cosine is equal to 0. So that could be above the axis or below the axis. Now, because this value is negative, that indicates that we should be below the axis. However, let's say you didn't realize that, right? So you would think to yourself, okay, it's either going to be 90 or 270. So the question would be, oh, well, which one is it? And the answer to that question would be, well, where does 0, -7 plot? Do you plot it up or do you plot it down? Do you go up 7 units or do you go down 7 units? You go down 7 units, so therefore it should be the 270. All right, so it's as simple as that. When it comes to something like 4, we have r equals the square root of 2 squared plus 2 radical 3 squared. I leave it up to you. The more complicated the computation, the less likely it is that you're going to want to do it by hand. So r equals 2 squared plus 2 rad 3 squared. This one isn't bad, but still, you may want to do it on a calculator. 2 squared is 4. Rad 3 squared is 3. So we're looking at 16 under the radical, which is going to give us 4. They said we're only going with r values that are greater than or equal to 0. So I would only want the positive r. All right, theta is going to be the inverse tangent of y over x, 2 rad 3 over 2, which corresponds to rad 3, which, based off of our knowledge of the unit circle, that could put us in the first or the third quadrant. And the reason why I brought up the domain component, if you were to put this in your calculator and do inverse tangent radical 3, it's going to come back with 60 degrees. In this case, that turns out it's right. The problem is, depending on where this coordinate is, let's say this was -2, -2 radical 3, that could put it in the third quadrant, in which case this would need to be 240 degrees, you know? So this is a possibility, because tangent based off of ASTC is positive in the first and fourth quadrant, but the inverse tangent only exists in the first and fourth quadrant. Well, really, we'll say the negative quadrant, you know, below the x-axis, and the first quadrant, you know. So how do you get that third quadrant when it's an appropriate answer? Well, not from a calculator, not from a Jedi. So what you would have to do is reason it out and say, well, where does 2, 2 radical 3 plot? Well, 2 radical 3 is about 3.5, roughly. So I would plot 2 comma, and this diagram is like a disaster now, but let me go purple. 2 comma, roughly 3.5. 1, 2, 3, somewhere around here. Actually, it's going to be precisely right there. So that would be 2 comma 2 radical 3. We know based off of just plotting that rectangular coordinate that we're living in the first quadrant. Because we're in the first quadrant and I have a choice between these two angles, 60 or 240, it must be the 60, right? So then I can now conclude that my final answer is 4 steps in the direction of 60 degrees. Now, if you get lucky, sometimes the radicals don't line up beautifully. Sometimes the answers just aren't nice. But if they do, you plot the radical and you say, oh, wait, whoa, hold on. Well, this is a clean answer here. 1, 2, 3, 4 steps. Then it's just a question of the angle. 1, 2, 3, 4 pi over 12. That's the same as pi over 3. Or if you're counting in 15ths, 15-degree angles, 15 times 4 is going to give you 60. All right? So either way, you would get it. So it's kind of nice. There's some cool relationships as it